the next talk, which will be given by Mihai Horanyi. So take it away.
Thank you. Next slide, please. So, as you might recall, the Earth is continually bombarded by 100 or 150 tons of interplanetary dust every day. They come in forms of meteor showers or small particles that decoupled from their original source and form the sporadic meteoroid background. The next slide, please. Scaling it to the moon, about 5 to 15 tons of interplanetary high-speed particles, 15 to 20 km per sec impact speeds, will bombard the moon. It has no atmosphere, so as opposed to the Earth, where you could enjoy shooting stars, if you are on the moon, they are directly hitting to the surface and generating plumes of dust, typically 200, 300, 400 meter per sec outgoing small particles that a tiny fraction of that is escaping. The majority of that is falling back onto the moon. And this is the gardening and the resurfacing and one of the primary processes responsible of shaping the characteristics of the regolith and also possibly contributing to forming the lunar atmosphere. Next slide, please. The mission, LDEX, Lunar Atmosphere and Dust Environment Explorer, was a short duration, beautiful mission, 2013, 2014. If you click on the, whoever is driving this, if you click on the top left, that is an animation, if it plays. If not, you just see the spacecraft. It was orbiting initially about the height of 200 kilometers and then dropped down to 100 and furthest away down to 50, 10, a couple kilometers above the surface, eventually crashing into the surface in April of 2014. It carried this small dust instrument, LDEX. An incoming dust particle generates a plasma puff as it hits the target. It's about 100 square centimeter. Electrons and ions are collected separately. They are separated by an electric field. And those two signals allows us to tell you how big the incoming particle was. Even at 200 kilometer height, this instrument was hit at least once per minute with tiny dust particles coming from the surface. The next slide, please. This is all the data we collected. The impact rate of particles as small as 0.3 micron in radius and bigger, hitting this instrument once per minute, or bigger particles, which is 0.7 micron in radius. On average, you had to wait 10 minutes to have a hit. I bring your attention to these blue lines. Those are special periods of meteorite showers that clearly had an effect on puffing up the density of the lunar dust exosphere. The next slide, please. This is the map or the density map of the model. On the left is all our measurements. The dark regions are regions where we either never visited or couldn't make measurements, or because of sharing observational time, we didn't collect data. But we could rebuild this into kind of an analytic extension. And on the right, this is what you expect the average lunar dust cloud to look, with a typical density at the surface of a few times 10 to the minus 3 particles per cubic meter. Next slide, please. These are the enhancements during meteor showers. A couple days ahead, couple days after the peak zenith hourly rates that you would observe on the Earth. You see the impact rates simultaneously, not skyrocketing, but certainly increasing as we fly around the moon. The next slide is the density enhancement during the Geminids. And actually, you could use the location of the density enhancements to find and identify which meteorite shower is the one responsible for the enhanced densities. The next slide is showing a combination of On the top, the impact rates, what we measured, and then the data from the ultraviolet instrument also on board, making a statement about the density of sodium and potassium atoms in the lunar atmosphere. The next slide is a comparison that it shows that the impact rate has an excellent correlation with the potassium density and has very little or no correlation with the sodium density. It also indicates that the potassium atoms on average have a lifetime of a couple of days, maybe 5 days, and then the cross correlation is maximized. That probably tells you more about the lifetime of potassium and sodium that you could learn from its response to enhanced dust influx rates. The next slide would have been a movie of a dust ejector plume, but somehow it doesn't translate. So let's just move on then to the next slide. This is the impact rate of a plume as if you were to fly through at various heights. These are 17 or 18 different plumes, and the higher the spacecraft was, the duration of a dust plume, the enhanced impact rates are getting wider and wider due to the natural spread in their initial velocity distribution. So now that tells you something interesting, because the structure of a plume allows you to project it back where it came from the surface. So the next slide, please, is imagine that you would fly over permanently shadowed regions. I have to remind you that as far as dust, interplanetary dust is concerned, nothing is shadowed. It is coming at all times, at all places. So imagine that you would fly over a permanently shadowed region with a dust instrument. You would certainly be able to look into these regions using dust. And when I mean look into, the next slide tries to illustrate that you could actually develop an instrument, and we have these in our labs, that in addition just to tell you the size of a dust particle, it can break the impact generated plasma cloud into a time of flight system and tell you the composition of the particle. On the bottom left is a Cassini example. This is a little faster, 4 km per sec impact of E-ring ice particles, and you see the sequence of protohydrates that you cannot possibly mistake ice or the water content of an incoming particle.
Two more minutes.
Next slide is the knowledge gap as I found them in the League report in 2016, and certainly there is a lot of issues about dust, as a resource potential and how to work and live on the lunar surface and so forth. I would like to add, of course, that we don't really know the meteoroid flux, especially to polar regions, and what exactly are its effects. Is it delivering volatiles? Is it actually removing volatiles? Or how does it contribute to the budget of resources that you might consider for ISRU in permanently shadowed regions? To close that knowledge gap, you could consider a polar orbiting spacecraft with a dust composition analyzer and a large area dust flux monitor somewhere on the surface to tell you what hits the surface, what speed, what size distribution, possibly what composition. So I have a summary slide. This is my last slide. Next, please. You know, the moon, as any other airless body or bodies with atmospheres, are continuously bombarded by micrometeorites. In response, the moon is engulfed in a permanently present dust exosphere. It is changing with time and location. The ejector particles are samples from the surface and provide an opportunity to map the surface composition from orbit and identify possibly regions that are high value for ISRU. Finally, if you were to consider a large area dust influx monitor on the lunar surface, that might help to resolve how to best protect the long-term presence of humans and machines on the surface. Thank you.